Thank you everyone for coming to my talk. I'm going to be discussing some new results involving convergence rates for non-smooth stochastic gradient descent. Let's begin with a simple one-line definition. So gradient descent is an iterative optimization procedure where you produce the next iterate by taking a step in the opposite direction of the current gradient. And even for an algorithm with such a simple definition, there are still some fundamental and basic questions that have yet to be resolved. So in this talk, we're going to learn about what these questions are, and then we're going to find the answers. But before we move into the definition of these questions, let's take a second to recall some standard results that you can find in your favorite convex optimization textbook. And in particular, I'd like to focus in on the setting where the function that we're optimizing is non-smooth and convex. And we see that in the non-smooth setting, the standard results involve averaging the iterates. Whereas in contrast, in the setting where the function that we're optimizing is smooth, then you can get convergence rates even for the individual iterates themselves. And another thing I'd like to point out is when the function that we're optimizing is both non-smooth and also non-strongly convex, then averaging turns out to be the optimal thing to do, in that no other first-order algorithm will beat this order 1 over square root t rate. And this averaging procedure uses the step size eta I is equal to 1 over square root I, and it turns out that this is the only step size that will give you this optimal 1 over square root t rate. So now let's gain a little bit of intuition about why the standard results for when the function is non-smooth require averaging. So if the function that we were working with is smooth, then it turns out you can tune the step size appropriately so that the iterates are monotonically decreasing in function value. But if your function is non-smooth, then the graph, the shape of the graph of your function can change rapidly, and therefore it's possible that iterate t plus 1 has strictly larger function value than iterate t. And usually to get around this, averaging procedures are used to avoid this non-monotonicity issue. So this doesn't preclude the individual iterates themselves from converging in function value to the true minimum of the function. And this question was posed as an open question in COL 2012 by Shamir, where he asked, what is the suboptimality of the last iterate returned by gradient descent? And he also posed a high probability version of the same question. So our work answers both of these questions in both the setting where the function that we're optimizing is strongly convex and also non-strongly convex. But for the purposes of this talk, we'll be focusing our attention on non-strongly convex functions. The results that we state have natural analogs in the setting where the function is also strongly convex. And now let's understand a little bit of the background story behind the first main question. So in 2015, Nesterov and Shikman gave an algorithm where the iterates values converge to the true minimum of the function at the optimal 1 over square root t rate. And it's important to note that the algorithm that they gave is not gradient descent. And so therefore it's natural to wonder whether the iterates of gradient descent also converge in function value to the true minimum of the function. And if they do they also get the optimal 1 over square root t rate? So in 2013, some progress was made on this question by Shamir and Zhang, where they proved that the iterates do converge in function value to the minimum of the function at a rate of order log t over square root t. And note that this is suboptimal from the optimal rate by a log t factor. And the question that we address in our work is whether or not this log t factor is necessary in the upper bound. So our first main result states that the log t factor is indeed necessary. And more formally, if you fix any time horizon capital T, then you can define a one Lipschitz function that lives in capital T dimensions, such that if you run gradient descent from the origin using the standard step size of 1 over square root t, you'll obtain for capital T consecutive iterations monotonic increase of the function value until you reach your time horizon where your error will be omega log t over square root t. Now let me make a couple of quick remarks about the statement of this theorem. Firstly, we use the step size eta I as 1 over square root I, and this choice is natural because it is the only choice of step size. As recall that I mentioned earlier, that is the only choice of step size in the uniform averaging scheme that gets the optimal 1 over square root t rate. Moreover, it turns out that if you knew your time horizon ahead of time, you can carefully tune your step sizes with knowledge of the time horizon so that the error of the last iterate is order 1 over square root t, which is optimal. And if you'd like to hear more about this exciting work, make sure you stick around for the next talk. So pictorially, what our result is saying is the following. This is an execution of gradient descent, a Python simulation of gradient descent on the function provided by our lower bound on the last slide. And here we fixed capital T to be 1,000. So the function that we're working with here lives in 1,000 dimensions. And as you can see, for 1,000 consecutive iterations, the error of the iterates produced by gradient descent is monotonically increasing until you reach the time horizon of capital T, where your error is log T over square root T. Okay, so now I'd like to move on to talk about our high probability results. And in order to do so, I need to define stochastic gradient descent. The only difference between stochastic gradient descent and gradient descent is that the gradient oracle for stochastic gradient descent returns to you a random quantity gt hat. And our only assumptions about gt hat is that it is a gradient in expectation and its norm is almost surely bounded. So now the error of stochastic gradient descent is a random quantity, and it turns out that the result from Shamir and Zhang also holds in the stochastic setting, so therefore they get an expected upper bound of log T over square root T. And our lower bound holds deterministically, and so therefore it also holds in the stochastic setting, and so our lower bound is also valid in expectation, so therefore it shows that this expected upper bound is tight in expectation. But this does not say anything about whether the iterates converge at this log T over square root T rate with arbitrarily high probability, which was the second main question posed by Shamir and Colt 2012. And so for the remainder of this talk, we're going to be focusing on this question. So it turns out that this 1 over log T over square root T rate does hold with arbitrarily high probability. More formally, if you suppose that you have a convex on one Lipschitz function, and you run gradient descent with a valid subgradient oracle, then your error at iteration capital T will be log T over square root T with arbitrarily high probability. So the proof of this result uses a generalization of Friedman's inequality, which we develop in our paper. So we call this the generalized Friedman inequality, which is a martingale concentration bound, which is useful when the total conditional variance, or the square function of your martingale, is bounded by the original martingale itself. More formally, if you let d1 through di denote the increments of your martingale, and you have that the following recursive property holds, where the total conditional variance of your martingale is bounded by alpha squared plus alpha times the martingale, you can bound your martingale by alpha with arbitrarily high probability. And so in our paper, when analyzing the error of the final iterate, we extract a martingale with this recursive property, and therefore an application of the generalized Friedman inequality yields the statement of a high probability upper bound for the error of the last iterate. And I'd just like to conclude now with a quick discussion of where our work fits into the landscape of other related works. And what I'd like to point out is prior to our work, we see that for all the return schemes that aren't the last iterate return scheme, there were lower bounds that matched the expected upper bound, and there were high probability upper bounds which were at least close to the expected upper bound. And there's a huge gap in knowledge prior to our work with what the lower bound and high probability upper bound for the last iterate were. So our work resolves this issue, and along the way, we also prove a high probability upper bound of 1 over t for the suffix averaging return scheme. And this high probability upper bound is used in the proof for the high probability upper bound of the last iterate in the strongly convex case. And it turns out that this suffix averaging high probability upper bound is the first high probability upper bound in the strongly convex case that gets the optimal 1 over t convergence rate. So I'd like to conclude there. Thank you everyone for your attention. We'll be at poster 168 at 6 p.m. if you'd like to chat.
Okay, thank you. And speaker again. All right. So more on this topic in the next talk, which is on making the last iterate of SGD information theoretic optimal.